On behalf of IEEE Bangalore Chapter, it gives me a great pleasure to welcome you all to this webinar on application towards indoor-outdoor localization techniques using radio frequency engineering. Myself, Dr. Jalaja, Chair-elect, IEEE CAS Bangalore Chapter, will be your host. I am privileged to welcome our today's speaker, Dr. Raed. I would also welcome our IEEE Execom members and our General Secretary, Dr. Parameshwari Achari sir, and respected participants. Now, I would like to request our Professor Parameshwari Achari sir to introduce our today's speakers. Sir, over to you, sir.
Okay.
Sir?
Okay, thank you very much.
Parameshwari Achari sir?
Wait, Professor. Hello, Professor, wait, please.
Yes. Do you hear me now?
1 minute, I will introduce, Professor. I will introduce.
Okay, no problem.
Wait. Ma'am, 1 minute, I'm getting there. Yeah. Okay. Dr. Raed Alhameed is a professor of electromagnetic and radio frequency engineering at the University of Bradford, UK. He has long years research experience in the areas of radio frequency, sensor design, signal processing propagations, antennas, and electromagnetic computation techniques. And he has published over 800 academic journal and conference papers. In addition, he is co-author of 6 books and several book chapters. At present, he is the leader of radio frequency antennas propagation, sensors design, and signal processing, in addition to leading the communications research group for years within the School of Engineering and Informatics, Bradford University, UK. He is a principal investigator for several funded applications to EPSRC, leader of several successful knowledge transfer programs funded by British Council. He has also been a PI and co-investigator in several funded research projects, including H2020 Mary and other research proposals. On behalf of IEEE CAS Bangalore Chapter, so I request and I thankful to Professor Raed for accepting our invitation to be the today's speaker. Thank you, sir. Welcome, Professor.
Thank you very much, Param. Thank you very much. Hello, everybody. I just want to thank everybody for the attendance, first of all, and the interest as well in localizations, especially for using radio engineering. So I will start sharing the screen, and I hope somebody will tell me he can. Okay, very good. And maybe it will be good really if I can work like this, or I can view it like that. Can you see it now, everybody? Baram, can you see it?
Yeah, yes, Professor. Yes, it's visible.
Very good. I thought it will be different page. Okay, very good. Usually, I just want to give a brief idea about the Bradford. So Bradford University, it is established as well a long time ago, and I think since 1960s, I think, and then changed to university as well, and then we work with a very good staff as well from the industry and the academia. Specialized as well in radio frequency and communications. What we have as well in Bradford, there are many as well faculties. So one of them, which I work with them, is the engineering and informatics. And there is health and management, law, language, and life sciences, industrial as well, engineering, all these as well within Bradford University. So it is a quite a broad subject taught in Bradford University. My area is I am electrical and electronic engineering. Work for more than 40 years as well in the teams of radio and propagations and communication and signal processing as well, which I am very happy really to give you more details on what we are recently doing in terms of localizations. So I'm leading the 5G communication research group and doing radio frequency and microwave measurements, research leader as well for antenna propagations and sensor design. We have a lot of work as well covering indoor, outdoor localizations. And at the same time, we have outdoor to indoor or indoor to outdoor localization of people. I think is stuck. Yeah, very good. So, state of the art to this talk. So I will cover as I can the localization accuracy using, for example, time of arrival estimations over OFDM, wideband spectrum. And then the second as well subject I like really to cover is the wideband transmission as well, direction finding using angle of arrival. Of course, over as well OFDM multi-carrier modulations. And we are going to test this one over adverse as well channel conditions. And we'll show you as well some results, some measurements to identify the advantage and disadvantage of these type of methods. Of course, I'm going to show as well low cost effective methods of tracking and monitoring, for example, patients, elderly people, people with dementia, for example. And I think most of you are familiar as well on how to monitor as well people. Usually mobile phone as well now, it is the best sensor we can use to monitor people. But however, we are adopting simple things like, for example, the RFID, and then we talk about the wearable and touchless RFID, and then maybe I can ask questions by end of that subject. And then I'll move to show you as well the results of what we have done by the end of a big project, European project actually 2020, on building, for example, the MIMO systems to operate on 5G. So as I said, I will cover these items, and then we'll give some nice introductions about the systems in 5G. The motivation for this talk, it is it's very hard to say, but there are so many type of services required really to identify, for example, the accurate positions or information from a patient to some terminal point. And then we need to decide about the accurate location information. And we need to be more energy efficient, really, to save the life pathway. So localization for indoor environments is very important. Localization as well in hospitals is very, very important. Because sometimes we got people, they cannot read, write, for example, and it will be good really to identify them through, for example, a simple sensors, and you need to track them where they are. And this is very important as well in hospitals and for example, in a market or in environments, people, they can lost, for example, their children. So we need just to have some information to get into it. So my aim is to enhance different indoor localizations. Of course, somebody will ask, why the OFDM? So OFDM is a moderation, can help as well to compensate, for example, the frequency selective channel to a multiple point of flat fading channels. And if we are trying really to use it, we need to be very accurate as well in synchronizing these type of carriers we are sending over the OFDM or over the orthogonal multi-carrier moderations. So in my view, so OFDM.
Views కూడా
Sorry.
పెట్టాలి.
Sorry. Okay.
18 views పెట్టనాడు టోటల్ గా.
Okay. Can I? Yeah. And then the OFDM is applied in a way as well to, I will show you as well later how the OFDM can helping us as well.
Views a flow chart plus what diagrams are existing now. Ask him. Time లేదు అంటే కుదరదు. అందుకే అడుగుతున్నా. I want the due date so I can.
You just unmute yourself. I'm sorry, really.
All participant to mute yourself.
Sorry, I can't. Can you mute yourself so I can continue? Thank you. Okay. So the idea is the OFDM can be applied in a way to provide some kind of titrations for the severe, for example, a channel within the indoor environments or even for the outdoor environments, which I am going as well to show you later on. Localizations is very simple, is we need as well either it will be 2 base station or it could be 1 base station, or it could be as well 3 base stations, or it could be 4, could be 5, could be 10. So localizations as well, if we need to be 1, so we need to have at the time is the other parameter, and then the GPS of the position of the sensor. It could be implemented in a way to help as well and make predictions where the person is. And this is exactly similar when we need to apply it for 2 base stations as well, or 2 transceiver, I can call it. And when there are 3, then it's very simple. Then the 3 signals, it could be in time, frequency as well, and in a way of the sectorizations we are applying at the base stations. Then we can identify from these 3 stations the positions or the localized positions of the sensor itself, or a mobile or anything. So this is in general. Now, what we need to do, we'll show you some kind of applications. Maybe people, they are quite familiar as well with this, but we are trying our best really to find a simple methods as well to operate, for example, the indoor localization. So first of all, I'm going to show you the time of arrival estimation using OFDM. And as I said, is OFDM is maybe we can use it for high data rate transmissions. As we said, is fighting the frequency selective fadings. And usually very simple to be generated. Is just a simple inverse Fourier transform at the transmitter and Fourier transform as well in the receiver. However, the OFDM needs some type of synchronization. We need to be able to solve the, I can call it misorthogonalities between the multi-carrier. So we taking this, we apply it on ultra wideband to mitigate, for example, the indoor multi-band. And from that, we perform the fast Fourier transform, inverse Fourier transforms in time. And then we take the frequency domain. So we will have two. We have the time and frequency, and we operate on both. And then we can identify, for example, by localize, for example, 3 transmitter away from the sensor. We can localize the sensor within inside, for example, a building. Now we'll give you an example. We have done it as well here in Bradford. This is usually the building, the third floor in University of Bradford, the Sham building. And you can see as well, here is the sensor. And this is, for example, the transmitters all over. And from these 3 transmitters, we can predict as well the positions of the sensor itself. And why are we doing the ultra wideband? Usually we need more accurate positions of this person, where he is exactly within a few centimeters as well. It's not necessary we need to apply it for people, but it could be applied for a store, a big store. We can identify, for example, elements or products in a big factory. And if we identify the sensor with some ID, then we can get accurate localizations of this product item in a few centimeters. Here is just a simple data. As you see from here is 4 elements. So we can create, for example, accuracy from the 4 access point. Then we can go ahead with 3, 1, 2, 3, 1, 2, 4, 2, 3, 4, and 1, 2, 4. So this one will give us some margin really for the predict the right accuracy as well for all the methods we are applying. So we can see from here when the bandwidth is 2 gig and when the bandwidth is 50 meg. We can see the accuracy as well within 2 meter to 2 gig within, for example, 7 centimeter. When 3 access point is located there. Now the question is, can we apply this in much dense indoor environments? Yes, of course, we can apply it. Can we use 3 base stations? Can we use 10? The answer is as well yes, because when the base stations is located somewhere on the wall, on the ceiling, for example, in different places, this will help as well to protect many items as well. You can see it from there, and we can localize the people. The bandwidth is very important as well. If the bandwidth is available, especially the ultra-wide bandwidth, we can talk about 100 meters or 150 meters with accuracy of, for example, a few centimeters to localize people. So it's a very good condition, really, we can apply. And at the same time, from the OFDM in the time and frequency, we can negotiable the accuracy, the path from the multi-carrier or this is for a single element, I can call it. But the multi-carrier will give us as well more opportunities as well to take the first path, or to take, for example, the first 5 or 10 and take the average, or take the maximum within the first 10. And from that, we can identify, for example, by simple mathematics, to have the position of the target. Here is the graphical. You can see it as well from number of carrier 256, bandwidth 2 gig. We can get a few centimeters. And when we have 500 top carrier with 1 gig, you can see it as well. It's possible really to locate the exact position. Here, for example, 16 carrier and 250 megahertz. Still, we have a few, for example, I can call it tens of centimeters. And it's possible as well to get more, like for example, here 70 centimeter error compared to within 250 megahertz and 16 carrier. This one will give us more evidence. If we go, for example, in number of carriers, we are applying an OFDM here, and the number of access points, you can see it here. So if we apply 4 access points, and if we apply 3, 3, 3, 3 as well as I show you before, you can see as well when the bandwidth is going more higher, then the accuracy, it will be much better. And if we got more carrier as well, covering that bandwidth 2 gig, we can as well identify the accurate locations of the person. And if we go more lower than 128 number of carriers, still we can get the positions right, but with an accuracy of 2 meters or even 3.5 meters. I think it is quite reasonable as well when we talk about indoor to even to the outdoor. Second part of the my presentation, to localize people as well, not necessarily people that are carrying the sensor itself, but we can put some kind of simple sensor on their cloth. We can swing as well these sensor on their cloth. Nowadays, we can put as well the sensors integrated within the cloth as well. For example, soldiers, nurses, doctors, patients. It's very simple sensors. What we have done is we fix some type of sensors on people. These sensors roughly very simple geometrical, flexible sensors. It could be very thin and could be sticker anywhere on the cloth of a person. And then we can talk with them through a base station, or we can call it a reader. And from the reader, we can get some synchronous time samples, and then we can measure the received signal strength, and then we adopt some algorithms, as I'm going to show you through a few slides as well from now, how we do this and how we apply the localization theorem for this. So we got some volunteers as well. You can see the sensors we can put in positions as well. Chest, head, hands, thigh, knee, foot as well, back, and we can distribute it. And then we can do a very simple model using receive signal strength. And then we adopt that one, we run it as well in wireless inside, and then we do the measurement as well. And from that, we operate the linear least square regression method to give me a good estimate with the some data. So we'll take this data and then we learn the machine how they are working. We took several approach of a person. It can be on the floor, on a bed, on lying on a chair, sitting on a chair, walking, or standing. Of course, we can go beyond this. It could be more, 10, 15 type of states. But it depends on what you are trying really to do, how you can identify these type of positions. As I said, for this we need just to have more volunteers. You can see there is a chap here as well. Now he's a doctor and he's as well he's head of subdivision as well in electrical engineering. And you can see the reader as well. We set it up to read this type of sensors data. After that, we got the data from different people as well, because we need to train the system. And we can see at the bottom of the table here how the RSS, for example, values for a walking reference vector, for example. So we can compare the data from the data we are collecting from people, from a test examples. As I said, the test examples, we have used children, tall people, medium, male, female, and we collect intensive data. And all this data is going through a data storage, and then we analyze it. So you can see here how the position, head, arm, waist, back of the data is recognized by the reader when we got the as a reference for the walk. And similar as well, we can do a reference for sitting, reference for sleeping on the bed, or reference on falling on the floor or lying on the floor. We can see as well estimation of patient sitting on the chair and lying on the floor. You can see as well the minimum value we are observing there from sitting test and lying on the floor. We can see as well when the walking test is, we do it as well. And you can see the comparison between them all. There will be like, for example, walking test and compared to standing, and walking test compared to sitting reference as well. And walking test with walking when we compare it to the walking data reference when the machine is learned what we are doing. Similar as well, patient lying on the bed for a period of time. Now, somebody will ask how long the period of time. Sometimes we use it, for example, 10 seconds, sometimes 5 seconds. But it could be changed as well, because somebody can tell from standing to on the floor within 2 seconds. So how we are going to treat this? Of course, we can as well, because the reader, we can adjust the time slots of reading to improve as well the data and how we can make the decision for that. Similar as well, lying on the floor, you can see. And what we have done to check as well the accuracy as well of the methods. So standing, for example, sitting, walking, and as well sleeping for 4 seconds. So all this has been done in one example. And of course, we got it right as well from the data set we have it. So we measure the Euclidean distance and the RMSE. We identify as well how the data for all this time is carried, the exact position and localization of that person. In conclusions, there are so many things can be done in time, frequency, different methods of optimizations like neural network. There are so many things, but as I said, I just give a few things here. It is simple, it is easy, but it is difficult as well to let people wearing some kind of sensors. So we need to think about something else as well. So we are thinking about wide communications as well to talk with the sensors. And then we try as well to publish this as well. I put the publication here for many, if somebody want to have more reading. More publication as well here. And then people they are thinking about wearable is very hard to mount it on people or on the cloth. It needs to be washable as well. So I invent with my PhD students, we call it touchless. So touchless is we can put the sensor on the wall or on the ceiling of the room. And then we can have the readers somewhere. Could be one reader, two, three readers. And from the reading data from these sensors, we can identify the positions and the localization of that patient. Really, we succeed as well from these data. I put two publications here. Still, the second one is not published yet, but is accepted. You can see it as well using neural network. So, in general, health is very important to monitor, especially with COVID-19. People, they take off from hospitals. They need to be monitored. Monitored, that means we need to have something. We got a problem as well of aging. So we need to monitor people and to see their conditions as well. Especially as well with people with chronic diseases. Localization is very important, as I said from the beginning. UN Word as well as stated in 2013. This is very important to be treated in a way really to improve and to save the costs from the health institution. So monitoring, it means monitor the activity of the patients. So we need just to think carefully. Within the time, we need just to think how the patient can be performed. Is he right? He's moving, he's sleeping, he's falling on the floor, somehow. All these, it needs to be identified. So we think about simple things here. So all these can be used: pressure sensor, electric motion, infrared, semi, RFID, and all these data can be collected. And in my view, we use all of them, but in general, for simple wireless communications, we've done the passive RFID to enhance, for example, the orientation and location positions of the patients. And then we drive a very simple flowchart. You can see it here. We can know the ID of the patients, and then we can overlap all these data in a way we can talk with the data from the sensors, and we produce some kind of reference data that we can compare with. So what I have done, and what my student as well, my researcher done, is we're taking this in a very simple, as you say, sitting, standing, lying, running, walking outside, inside the room, using the bathroom, for example. But before we go to practical side, we need just to make sure everything in the model can be work. So what we have done, we model a room, for example, with a bathroom, and you can see the sensors at the ceiling of the room, and you can see as well the RFID readers as well is distributed Sometimes we use 1, 2, 3, and then we synchronize them in TDM, which is very simple really for us. The only things we have a problem of cables to distribute the power and the cables to the readers and to the USB power transmission. So here you can see is empty. Here the patient is on the bed. Somebody will ask how we can model the patient. Patient is full of water, so we assume a very simple cylinder or rectangular box with a very simple relative permittivity and conductivity of water. And then we decide how to read from the data from the RFID sensors. We do it here as well, experimentation, when the patient is in the bathroom. You can see it here in the bathroom. It's there. And similar as well, when he is standing, sitting as well. And when we got all this data, then we got the average accuracy of all these data from different run of the model. And we can see we have roughly about 85 or 80% or 81% accuracy within a very simple number of sensors, not touching a patient. So we can call it touchless. This is the way of how the sensors, they are distributed the power over the room. When is nobody there in the room. So no patients, the room is empty. So we got plenty of data. And the subject, for example, when the subject is in the bathroom, you can see the pattern has changed. So machine learning is putting it through really to work to define the differences between them and to make a decision. And this is what we have done. Similar as well, when the subject is lying in the bed. So this is the view of the distributions of the power spectral in the room, reading from all these sensors. Usually we are reading from the reader, but we assume the power compared to the sensor itself. That's why you can see it as well is a very nice figures to show us a two-dimensional functions, which we can make a very good decision. Similar as well, where subject is standing. All has been done. And then we went to the practical. So practical, we have done something very simple. You can see the wall there is we fill it up with so many sensors in horizontal and vertical. Sorry. And then the patient will exist in the middle, either standing or fell on the floor. And we have done it for many people. We got it as well. So this is estimation on the power and the number of the sensors. We have done it. And then we are able really to make a decision after that. So we try to do all these. You can see it from 12 type of states. And we identify two things as well. So the mean average of the Gaussians, and then the type of the classes of the variances of the actual data. for many people. We have as well every two frequency distributions of the Gaussian distributions of all the data. So data for different classes, standing, sitting, and you can see it is all is a Gaussian distributions, but usually they have uh, they have the idea from reading the data with different type of lemma, for example, estimations, functions, ready to identify the state of the position of the person. I'm sorry, is it still stuck? So here as well for different classes, and this is the, for example, frequency distribution of Gaussian score. There is quite little bit differences as well, but they are showing a very nice Gaussian parameters to learn between all the states we are getting it through. Then predict the class algorithms, as I said from the beginning, we got the mean and the matrices of the variances of these Gaussian distributions. After that, we because activities they are Gaussian distributions, then we adopt lemma, which measure the data sets of same activity have homogeneous but not the exact Gaussian score distribution, because there is a little bit differences between them. Especially there are so many states, they are very close. So lemma has identified the type of the classes and the sample of the data set, and then perform another class of the activity and then compare it, which give us more accurate decision in making decisions really for us. And then lemma is applied, and you can see as well how the states compared to the Gaussian data we are collecting, and identify the classes accurately from a position from a set of data where a person can be exist in the room. Similar as well for the fourth. Similar to the other fourth as well. We can see here is the minimum. We can see here the minimum. We can see there the minimum. So all these has been defined using lemma. However, we have done as well performance evaluations of the data. So in terms of accuracy, precisions, recall, and I think you know the rest is we talk about root mean square error of the data collector. So performance evaluations from judging of the data, because we know it, we have done it, there is no error, and then we can see the conversion matrix as well. From that is a little bit of mean damaged, but still the accuracy with a 95%, 95% for the state, for example, 6, 4, 2, and 10 as well. Still, the work, the target class is meeting the predicted class as well. We are trying to change. Here is a simple as well data from all the 12 states we are producing. You can see the precisions mostly likely is 97% and above compared to what we have done when it is wearable. The F score as well is a brilliant. It's 97% to classify the data. We can see as well the root mean square algorithms between the predicted and measured. And when they are very closely the states between them, standing, walking, for example. So we can get a good result as well to identify the differences between. Again, as well, effect of object occlusions as well. So without object occlusions and with object occlusions as well. So when something like null line of sight exists, it will be a little bit problem as well for the readers really to read the accurate power. That's why we lose a little bit of the accuracy. Compared to other methods as well, well known in localization, like random forest, logistic progression, SVM, and our proposed method can go to nearly 98%. As well, it is simple. No need to put it on a paper. It can work with 97%. It can carry so many things. We are trying as well to put it as a simple solution to guide the people how they are performed when they are isolated. So approach to health monitoring is the best. So we can be more accurate as well in terms of position and orientation of people and the rate of change of the states. So it's very important. Of course, this one can be integrated with other sensors to improve, for example, the accuracy. Like, for example, heart rate or blood pressure or something indirectly from these type of sensors to the base station. Good questions for everybody. Do you think you are able to monitor pressure without using tags? It's very difficult, but it's not difficult. We are as well working on this. So simply without tags, we can monitor as well people. Using routers, wireless routers only. Could be like a radar. But it needs as well to learn these routers. I'll go to fourth part of my talk. So this is a smart tracking based on OFDM. Sorry, I got a very bad cold, but it's not COVID-19. It is good. So this one is smart tracking. We have done it as well. We put the sensor underneath the car for outdoor environments. And then we put the channel modeling for all what we have done for channel dispersion model. And then we measure the angle of arrival from that model. And then we predict as well the location of a sensor from a distance. And we adopt as well algorithm to predict the K-factor distribution for urban area, for suburban area as well, even for rural area. And these can be found as well within IEEE transactions of our work on localized people from a distance of 15 miles. And then I go within the kernel, I got a very simple algorithm, but still I'm using OFDM. This is a very new work. It's already published, I think, this year. And we provide some kind of sensors on the cars or on within, for example, a simple device. And we test this one inside the NA chamber. You can see it there. This is the radiations as well. This is the localizations when we ignore and make matching for the array coupling, because we need just to make it more smaller. And now we'll give you nice examples what we have done. So we need to look at this person here, and we are moving in a car. This is Leeds, by the way. Leeds city center. All these buildings. And we done the model and we done the measurement as well. So I will show you, this is the OFDM. You can see the OFDM carrier. This is the face as well. This is the carrier. And now the car is moving and is predicting from what we can see, and similar, we can get to the end of getting that. So all these, it can be done for outdoor environment using OFDM. Of course, we apply here one spectrum, which is roughly about 400 megahertz. And then we go beyond this. So the other problem here is my office in Bradford University. And we did the start point here. So we did the models and we done the measurement as well. And you can see the car is moving in 3D. And we can make a decisions as well. All over. And because my office in the 3rd floor, it will point as well where the maximum reflections from the wall is compensated to that. I can say localization is my big area really to improve as well later on. 5G is coming to the way as well. 5G can enhance more as well bandwidth and data rate, which I think it will be more coverage as well, will enhance, for example, the localization. I think I will stop here. Okay, Baru? Jalda? Can you hear me? Jalda?
Yes, sir. Yes, sir.
I can stop here. Thank you very much.
Thank you, sir, for your wonderful information about this webinar. So I request a participant, if you have any questions, please type into the chat window. Otherwise, you can unmute yourself. You can interact directly with the speaker. Hello?
Yeah, I hear you.
Yes. Anybody is having any? So one question is there, sir.
Yes, sure.
Can I read out the question?
Sorry.
So will it the advantages to use FRFT in place of FFT in localization using OFDM? The question, sir. Dr. S. Pratap is asking.
Yeah, can I, because I didn't hear the
Sir, the questions are there in the chat window, sir.
Oh, right, okay, okay, I will, no worry.
Yeah.
Kindly provide us material and video recording there themselves. I think for the materials, most of the work has been published. And I believe there are, I believe all the information is on the web. If you go to the Google Scholar, really for myself, most of the publication is there, or I can supply you with the link with the Bradford University regarding the type of publication, which is it has a green publication, clean publication, so everybody can read it straight away if you haven't got access to the IEEE Explorer. The second questions, let me just read.
Participant, unmute yourself. Sir, if it is a disturbance, you can't hear them. Please unmute yourself.
They said it will be advantageous to use FRFT in place of FFT. Of course, you can use anything really just to improve it. Just be careful as well. We need to use the bandwidth more efficiently. So OFDM, I think, overlapping the carrier is much better at the moment. Can you tell me which software? Okay, software is used we use message site software, and on top of that, we are using as well MATLAB program. On top of that, we are using different software as well for sensor design. Can you tell me which software? Okay, please share the presentation. It's already there, I think. Maybe I can put the PDF for you.
Sir, in question and A, Q&A window, there are 3 questions. Please look at that, sir. For Q&A window.
QA window. I can't see the QA window.
There is a question. Can UWM detect the distance without a receiving antenna per that one? Example, detect human from a distance.
Can you repeat it for me, please?
Yeah. Can UWB detect distance without a receiving antenna per, for example, detect human from a distance?
Okay, good questions. Really, is ultra-wideband can be used because ultra-wideband can work as well for I can call it 3.3 or 3.4 till 12 gig. So it's not necessary to use all this bandwidth. So as I show you, a good examples between 50 to 2 gig. And I assume within 1 gig or even 1 gig or half gig is quite sufficient really for localized in a very severe, for example, indoor environments, looking for example, a concrete wall. Because in ultra-wideband, we need just to have quite a number of base stations. And these are very important really because we need to have the diversity of the wide spectrum to be propagated. So my understanding, the advantage of that is to have 3 to 4, for example, in area for a small building, for example, or even more is much better. But the only thing is you need to write a code as well to control these transceiver altogether.
So next question, sir.
There is another question, I think here they say for OFDM implementation with varying number of subcarrier, how much processing time is there difference when subcarrier 16 and when subcarrier 2000? First of all, we haven't got 2000, we got 2048 if you wish, because we are working with the fast Fourier transform. So usually is very good questions really. As I said, 60 carrier, it could be as well. We will have a facing some kind of frequency selective channel. So it's not necessarily all penetrated, I can call it. But when we talk about 2048 carrier, so I assume the channel, it could be more flat fading compared to what we are facing as a frequency selective fading. Okay. Again, as well, on the accuracy, we must have the number of carriers more higher. Unless otherwise, you need to increase number of base stations to get more accuracy on the buses. He said, thank you for taking my question on Android. One more question, please. If there is no line of sight, will RSSI be? Very good questions. Very good questions. Usually, we have not necessary we have line of sight. Not necessary. Because what we have done, we can show you as well. Sharing. So what we have done here, there is no line of sight here. There's no line of sight. But we have a path. It's coming from there. And I just, if I want to run it again, you can see there is no path directly to that. So we got only this path, which is reflected from the wall. And that's why we drive the car in that position. So the car is moving to that. And you can see as well, there is only one wave incident. But we know it's somewhere there. And we moved to make a decision. So it's not necessary, as I said, to have line of sight. No, not necessary. Of course, the accuracy, it will be much less, but not much less in hundreds of meters or 50 meters. It could be within a fraction of few meters as well. Okay. Any more questions? Let me just go back. How to go back? Is stop this one.
Sir, in the Q&A window, you can see, sir, two more questions are there.
Yeah, sure. I just want to go back to really,
Can I read out otherwise?
start sharing. Yeah, you can ask me. Yeah, sure.
When
said,
when line of sight may not always be available, would
this is my
RSSI?
answer. I answer it.
Yeah.
I said it's not necessary. We have only line of sight. There is no line of sight. We are working on non-line of sight. I told you when I share the when I show you Leeds city center, there is no line of sight, totally no line of sight. And the method is working perfectly. We are working on the path, wherever it is. And then we decide how to move further, how to move. Okay? And I show it to you as well because let me just show it again as well for the people. Maybe they, so here as well is there. Is here. There is no line of sight. 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 Here, line of sight. Only here, line of sight. I hope this is clear for everybody. Will it be advantageous to use 3D array in place of 2D array? Very good questions, really. Is 3D is much better as well. Of course, it's much better. Of course, we are, when you are using ring array, is more sufficient really to give you the other third dimension, as I showed to you. In this tree, always they are looking for a flat, to put it on the top of the car, for example, or to be carried by hand like that, carry it by hand, or put it on the hat here. So this one, it could be a very nice base station on a hat, small one. So 2D is more preferred to the industry, more preferred. But of course, 3D, it will be more expensive and the volume will be more large. Of course, what is your opinion on machine learning? Machine learning is beautiful. It's very good. Without machine learning, we cannot state the differences as well between the Gaussian data we are collecting for 12 states, which is very difficult. It is a good way to indoor localization. I will say, of course, yes. It is very good. It is more dominant. But you need as well to more data to learn as well. More data to let the system knows what he is doing. And you need to measure as well the confusion matrix for that particular data and how much data they can get. I think the best is not to go less than 95% precisions of the data collected. Along with MATLAB, what are the other software are used? Okay, very good. I use so many software as well. I starting from ADS, Advanced Radio. I used as well CST. I use HFSS. I used Wireless Insight. I use MATLAB. I can't remember really. There are so many things, but this is the main software we are using at the moment. So I can call for neural network and this and that. Usually we are using MATLAB. But for propagation channels and this and that, we are using other type of softwares like wireless insights, really to define the model inside the rooms or a building or outside as well. Okay. Oh, thank you very much. Thank you for your interest as well. I think there is no more questions to answer.
Okay, sir. Thank you. Thank you very much, sir, joining us
I-
and giving guidance for a very good research topic. Thank you, participant. We'll see you. We'll meet again in another event. Okay, thank you, on and off.
Absolutely. I'm sorry, really, I haven't got time. And as I said, I got a cold. I
Okay,
can't,
sir.
but I didn't show you the 5G, what we have done, because 1 hour is gone. And what I'm thinking, maybe next time I will talk about the 5G in details, really, for all of you. No problem.
Sure, sir. Sure. Sure. We're looking forward to you, sir.
No problem at all. Thank you very much.
Thank you, everyone. Thank you very much, sir. Good
Thank
night.
you.